Hello students, in this video we'll consider Scherk's minimal surface. So Scherk's minimal surface is a classic example of an example using the Weierstrass-Enneper parameterization. And it's given by the following parameterization. R of u and v is going to be the argument of zeta plus I over zeta minus I, the argument of zeta plus 1 over zeta minus 1, and then finally the log of the modulus of zeta squared plus 1 over zeta squared minus 1, like that. Okay? So this takes a little bit of work to unpack. I'm using our classic idea over here that says what? That says zeta is really u plus iv. So I'm complexifying the parameterization space. Okay? Excellent. And so now, make this, let's do this in the calculation over here. So what do we know about zeta plus I over zeta minus I, right? Well, this is going to be u plus I v plus 1, like that because I have an extra v, over u plus I v minus 1, right? And so this is going to be what? And so if I look at the numerator of this, so what can I say? So if I multiply this expression by u minus I v minus 1 over u minus I v minus 1, we get this is equal to 1 over the denominator, right? The denominator is irrelevant for the argument calculation. I'm going to have a u squared and then plus v squared minus 1. So it's going to be a u squared plus v squared minus 1, like that. And then we're going to have what for the imaginary terms? The imaginary terms are going to have a, let's see, we have a u times v times negative I. A u times v times I, good, and those are going to cancel out. And then we're going to have a u and then another ui, so then plus 2iu, right? And that implies that the argument, the first entry over here, of zeta I over zeta minus I is equal to the argument of these things is going to be equal to the inverse tangent of what? The inverse tangent of just a 2u over u squared plus v squared minus 1, like that. Great. And then similarly, so if I replace I with 1 and negative 1, so similarly, we have the argument of zeta plus 1 over zeta minus 1 is going to be equal to, now I get the imaginary part of the v, right? So I'm going to have a negative 2v. It's going to be negative 2v over the same thing for the real part. It's going to be the same exact expression. U squared plus v squared minus 1. Beautiful. So now I have the first two entries of my parameterization space. That's going to be the inverse tangent of this thing, actually, right? So I need a tangent inverse in front of this guy. So put tangent inverse in front out. Tangent inverse of negative 2v over u squared plus v squared minus 1. Okay, now this is going to take a little bit of doing over here, so let's do the next calculation. So now, let's look at zeta squared plus 1 over zeta squared minus 1, which is going to be u squared minus v squared and plus a 2uv plus 2iuv plus 1 over u squared minus v squared minus 1 plus 2iuv, like so. Good? And so now the key behind this is, let's simplify this a little bit because we need to find the real and imaginary parts of this, and then we're going to have to find the square root of it, right? So this is the only hard part of the problem. So then we have a, I'm going to do u squared minus v squared minus 1, and then a minus 2iuv over u squared minus v squared. Is it minus v squared or plus v squared? Yeah, minus v squared, right? Minus v squared plus 1, minus 1, of course, right? That's a minus. Minus 2iuv. Okay? So let's do it carefully. So what we'll have over here is the denominator is going to be the following. So let's look at the numerator. So we're going to have a, slowly, so this is going to be a u squared minus v squared, then a plus 1, and then a u squared minus v squared minus 1. Okay? Those are multiplied out. And then we're going to have a, let's see, we're plus 4u squared plus 4u squared v squared. Then we'll put the imaginary terms over here. The imaginary terms over here are going to give me a 2iuv times this expression. Let's go plus 2iuv squared minus v squared minus 1 plus what? Plus a relative minus 2iv. What then a u squared? So then a u squared minus v squared plus 1. Great. All divided by u squared minus v squared minus 1. And that's going to be quantity squared plus 4. And we're going to have a u squared b squared b squared. Now, most of these imaginary terms are going to cancel out over here, right? So let's think of what we're going to have over here. So let's look at terms carefully. So if I look at these little block terms over here carefully, right? Those terms are over there. Okay. And then what's going to happen over here? So notice that these terms over here are equal now. So those terms are going to cancel out over there, which is beautiful. And then so we're going to have a minus 4i uv over there. The imaginary. So the imaginary terms are going to simplify to negative 4 iuv like so. Right? Great. Okay. And then what are these terms going to simplify to? So I'm going to have a e to the fourth, a b to the fourth, and a negative 1, right? And then so let's just do it carefully over here, right? So these terms over here are going to give me what? So let's look at those blue terms over there. It's going to give me a u to the fourth, then a minus u squared v squared, then a minus u squared, like that. Reverse terms. Then we're minus u squared v squared. Then we're going to have a plus v to the fourth. We're going to have a plus v squared over there. Beautiful. And then plus u squared, and then a minus v squared. Those terms are going to cancel, and then 1, and then I'm going to add 4 u squared v squared like that, right? So the v squared is going to cancel, the u squares are going to cancel, and then over here we're going to have what? We're going to have u to the fourth, b to the fourth, so u to the fourth minus, or plus now, how many u v's, right? So we're going to have a 2u squared v squared, like that. And then a what? And then we're going to have a factor of, let's see what we have over here. Let's make sure we have everything in the right spot. Good. Okay. And then finally, those are going to cancel with those. Perfect. And then we have a minus 1 like over there. All right. And then also a b to the fourth. So let's simplify that. Okay, and so now the question, let's do it in sort of simpler way. So what we can do, of course, we can think of this as u squared. We can think of this as u squared plus v squared plus a v squared minus 1. Well, I just sort of removed that, right? So just leave it like this. Okay. All right, excellent. And so now that's good. And so this is going to be what? So this is going to be a total of u to the fourth plus v to the fourth, and then a plus 2u squared v squared, and the minus 1. Okay? And these terms are very, very nice to write out as well. Right? Write that as plus u to the fourth, u squared plus v squared, quantity squared, right? And then a minus 4iuv, all divided by what? All divided by u minus v, u squared minus v squared minus 1 quantity squared plus 4u squared v squared like this. Okay. All right, excellent. And so now, let's write this in one following way. This is u squared plus v squared minus 1 minus 4 iuv, all divided by 1. All divided by u minus v minus 1 quantity squared plus a 4u squared v squared, right? And then so what happens is the logarithm of this thing, so now what's going to give me the following? This is going to give me the following. It's going to give me, when I do the log of the modulus of this thing, and a square root everywhere, so I'm going to pull it 1/2 out. So this is going to tell me the third component, this third component over here, this log of the modulus of zeta squared plus 1 over zeta squared minus 1 is going to be 1/2 the log, what? 1/2 the log of the modulus of this thing, so it's going to be this thing squared over this thing squared, right? So that's going to be a u squared plus v squared minus 1 quantity squared over here. quantity squared, minus 1, that's my real part, that's quantity squared, plus the imaginary squared, it's going to be a 4uv, or u squared, 4uv, quantity squared. Make sure everything was good. Squared. All divided by the denominator squared, right? U minus v minus 1 squared plus 4 u squared v squared 1 squared, like that. Cool. And so now we can check it. So there's a relationship between these over here. So it turns out that you can check. Now it's going to be, it's an algebraic pain to check this, but it's actually valid. That the z component, so if this is my x component, this is my y component, and this is my z component, that we can see is we can see that z is equal to the natural log of the cosine of the y component over the cosine of the x component. And now the question becomes, that we have this relationship between z and y, and unfortunately you might say, well, how am I going to relate the logarithm of these things? Well, the whole point over here is that, tangent inverse, if I have the tangent inverse of a number over here, alpha, and I can put the cosine of that number over there, what this is exactly 1 over the square root of 1 plus alpha squared, like so, right? So if I have the ratio of the cosine of the log of y, this is really what? So in other words, this cosine of the log of y, this is really equal to what? This is really equal to the natural log of what? Cosine of y, cosine of x is going to be the square root, and plus square out of everything because there's square roots, and put the apple on top, which is going to be this thing over here squared. My x is over here I, so it's going to be this thing over here squared, so it's going to be u over 2 u squared plus v squared minus 1 quantity squared, relative to what? Relative to this denominator over here. Negative 2v over u squared plus v squared to the negative 1, and this whole thing is quantity squared as well. And I don't need squared anymore. Yeah, but I achieve. Good. All right, and so of course, with a little bit of algebraic legwork, we can show these two things are equivalent to each other. Excellent. Okay, now the last thing to check actually, if this thing satisfies the minimal surface equation, right? Even though we know it comes from the Weierstrass approximation, let's recall what the PDE is of the minimal surface equation. It is 1 plus zy squared, and then zxx minus 2zx zy zxy, and then plus 1 plus zx squared zyy. In this, it becomes this function z over here. Our function z is really what? Our function z is really just the log of cosine, the log of the cosine of y, minus the log of the cosine of x, right? So I did an xy derivative of this thing. An x derivative of this thing is going to have no y's in it. So the whole sums over here are just gone, right? Partial z, partial x is going to be just something that involves x, and so the y derivative of that, it's now to zx. So what will zx be? So zx over here is going to be what? Is going to be negative 1 over cosine times negative sine, so that's going to be just a tangent of x. And then what's zy going to be? Zy is going to be negative sine over cosine, which is going to be negative tangent of y. Okay. And then what's zxx? So zxx is going to be secant squared of x, and then zyy is going to be negative secant squared of y. And so now, of course, the key feature of this is that this over here is 1 plus tangent squared. 1 plus tangent squared is going to be secant squared, right? So I have secant squared, that's going to be secant squared over the, that's going to be a what? That's going to be a secant squared of, that's going to be a tangent squared, sorry, excuse me, that's going to be a tangent, 1 plus tangent of y squared. So that term is going to be a tangent squared of what? It's going to be a tangent squared of, let's have 1 plus tangent squared, right? So 1 plus tangent squared is going to be what? So this term over here, 1 plus tangent squared is secant squared. That's going to be a secant squared of y, secant squared of y times what? Times zxx is secant squared of x, minus what? Then plus over here, plus 1 plus zx squared is going to be a 1 plus, that's going to be a secant squared of x times zyy, which is going to be a negative tangent y. So I made a mistake here, so let's grab over here. So we're going to get, let's be careful about this. So let's see. So this is going to be this term over here, zx secant squared. I mean secant squared times tangent y. Secant squared x. And then a 1 plus dyyy is going to be a tangent squared y. And then plus what? And then plus dyyy is going to be plus to the x squared is going to be plus tangent squared x. And then a negative secant squared of y. There we go, much better, okay? Now exactly, this is of course going to be the what? That's the secant squared of x, that's the secant squared of y, and so this is just going to add to the zeros. Proven that this graph over here, the log of the cosine of y over the cosine of x, which is basically by this long calculation, by this Weierstrass-Enneper parameterization of the Scherk surface, gives us a functional form of a graph of a minimal surface, at least in locally on regions that are bounded by rectangles of squares of size pi by pi, right? This will give me a parameterization of a minimal surface, and this minimal surface basically will have to have what? It has zero mean curvature over here, and it actually locally is the graph of this function. So it's a beautiful example of combining the Weierstrass-Enneper parameterization with using the minimal surface PDE with properties of analytic functions. Thank you very much.